we'll be talking about Chapter 5. And here's our little intro to Chapter 5. How do we measure distance traveled? Total distance traveled. So in this section, we're going to figure out the answer to this question by looking at the much-awaited sequel to the zombie race that we did on the first day of class. Okay. So our old friends, the zombies, Feynman, Hertz, Noether, and Planck, decide they're dying to run another race. After all, they have lots of time on their shriveled hands. So this time, the graphs below give velocity. So on the first day of class, they were distance time graphs, right? So today we're looking at a velocity graph. How is velocity related to distance? It's a derivative, yeah. Velocity is the derivative of distance. So kind of keep that in the back of your mind. So these are velocity graphs, telling you how fast each zombie was running, what their speed was at any moment in time during this race. So I want you to study the graphs, discuss with each other, and answer these questions about the zombie race. All right, let's discuss these first three together. Looking at look at Feynman's race. What was his strategy? Constant pace. How fast was he running? 1 mile per hour. Okay, so Feynman ran constant speed. 1 mile per hour. Okay, how about Hertz? What did Hertz do? Slow and then sped up at a constant rate. Good. And then sped up at a constant rate. All right, how about Noether? Yep, started fast and slowed down at a constant rate. How about Planck? Started really fast at 3 miles per hour. Slowed down until he reached a dead stop after 2.5 hours, and then sped back up. So Planck started fast, slowed down to a stop, and then sped up. Fast, slowed to a stop, and then sped back up. Good. All right, looking at Feynman's graph. He's kind of the easiest to analyze. How far did Feynman run? 5 miles. How do you know that? Yes, he ran for 1 mile per hour at a constant speed for 5 hours. And we had that old formula, right? RT equals D. So if you multiply 1 mile per hour times 5 hours, that would give you 5 miles. All right, so Feynman, we can use RT equals D because the rate is constant. But with Hertz, his rate is changing over the 5 hours. So we can't use RT equals D because what would we plug in for R? Yeah, an average speed? Okay, that would work. What's his average speed? 1, yeah, because before 2.5 hours, he's going a little slower. After 2.5 hours, he's going a little faster than 1 mile per hour. We could say that Hertz is traveling at an average 1 mile per hour. So then we could still use RT equals D, plugging in average speed for rate, and we would come out with, again, 1 times 5 is 5 miles. In this case, it does look like 1 is the average speed will work well, right? But we can't be absolutely positive that that's the exact distance traveled if we're not using the exact speed, using kind of an estimate. All right, so that's a good approach. Did anybody do something different to figure out how fast Hertz was running? Well, the slope of that line would tell you his acceleration, because this is a velocity graph. So its derivative would be acceleration. All right, so here's a method that we could use. So I'm sure that other people had other approaches for coming up with Hertz's distance traveled, but now we're going to use another method. So we're going to come up with an underestimate for how far he traveled by looking at each hour separately. And if you look at the first hour that Hertz ran, he started running at a half a mile per hour, and he finished running at about 0.7 miles per hour. So if we assume that he ran at a constant rate of half a mile per hour, then we could use RT equals D with a half mile per hour, but it would be an underestimate because he actually sped up. But if we assumed that he stayed constant at that first speed, we could use RT equals D on that hour. And then we're going to do the same thing on the next hour. He starts at 0.7 and finishes, I don't know, 0.9. If we assume that he just ran 0.7 the whole time, instead of speeding up, then we can use that constant speed. We can use RT equals D on that hour. And if we do that on each hour, assume that instead of speeding up, he stayed the same on each hour and use RT equals D on each of those hours. It will be an underestimate, right? Because we're assuming that he went slower than he did. So this is the new step function. And we'll say for the first hour, rate times time will be a half the rate times the time of an hour. And then my second interval will be 0.7, which is my rate times my time of 1 hour. And then on my third interval, looks like 0.9 for my speed for 1 hour. And then my fourth interval, I don't know, 1.1. And the last interval, 1.4. Oh yeah, that makes sense. 1.3. That's a good point. If he's increasing if his velocity is increasing at a constant rate, each hour it should go up by the same amount, and it's been going up by 0.2. Good. So then I add 0.5 plus 0.7 plus 0.9 plus 1.1 plus 1.3, and what do you get? 4.5? Yeah, 4.5 miles, right? Which we know would be an underestimate because we're underestimating his speed on every interval. Okay, now we want to determine a high estimate. So instead of assuming that he went his slowest over the whole interval, we're going to assume that he went the fastest over the whole interval. So over this first hour, he starts at 0.5 and ends at 0.7. Imagine that he ran the whole interval at 0.7. And then for the second hour, imagine he ran the whole interval at 0.9. And then the whole interval at 1.1. Then this whole interval at 1.3. And this whole interval at 1.5. So look at his fastest time over each hour interval and assume he ran the whole interval at that fast time. And we get a step function that looks like this. And we'd have 0.7 times 1 plus 0.9 times 1. So that last interval now is at a height of 1.5. So when I add those all up, what am I going to get? 5.5. And we know that that's an overestimate of the actual speed, because we are on every interval, we're overestimating his speed. We know he didn't run that fast the whole time. All right, so I want you to repeat this exact process for Noether. Get an upper estimate and a lower estimate for her distance traveled using this same method. Okay, looks like everyone did pretty well with Noether. So let's do for Planck. Okay, we'll do this one together. So we're breaking his race up into half-hour intervals. And so we're going to be adding up 10 values, right? We have 5 hours, half-hour intervals. It's going to be 10 values. All right, so we'll start with an underestimate. So I'm going to go back to the picture. Okay, so I'm breaking this up into half-hour intervals. So I'm going to put in my marks here. All right, if I'm looking at the first half hour, at time 0, he was running 3 miles per hour. And at time t equals a half, he's running at 2 miles per hour, right? So he started fast and slowed down. So what's the slowest that he was running over that whole interval? 2 miles per hour. So we're going to assume, since we're looking for an underestimate for how far he traveled, we're going to assume his speed was the slowest it was on that interval for the whole interval. Okay, and then from t equals a half to t equals 1, he went from 2 miles per hour to a little over 1 mile per hour. So if I'm looking for an underestimate, I'm going to assume the slowest speed. I'm going to say, okay, well, he went from 2 to 1-ish, 1.1 maybe. And we're going to say that he traveled 1.1 the whole time. If he went 1.1 the whole time, we will definitely get an underestimate for his distance traveled, if we assume that he went the slowest on that whole interval. All right, and then from 1 to 1.5, he started at 1.1 and finished at about a half. Assume he went the slowest, his slowest speed over that whole interval. So we're going to assume that he traveled for that whole half an hour at a half mile per hour. Even though some of the time he was going, most of the time he was going faster than that. We're getting an underestimate, so we go with the slowest speed. All right, and then from 1.5 to 2, he started at a half mile per hour and finished at 0.1 or 0.2. So we're going to assume the slowest speed for the whole half an hour. And then from 2 to 2.5, he went from really slow, like 0.1 or 0.2, to 0. So we're going to assume that for that whole half an hour he was resting. Right? He was at 0 for that whole half hour. And then from 2.5 to 3, his slowest speed was 0. So we're going to assume that he sat for that whole half hour there as well. So we're assuming a whole hour of sitting still now, based on 1 moment of sitting still. Okay, but we're getting an underestimate. All right, so then from 3 to 3.5, he started at about 0.2 and finished at about 0.5. We're going to assume he went 0.2 the whole time. And then for the next half hour, he's going to go 0.5 the whole time. And then the next half hour, 1.1 the whole time. And then the next half hour, 2 the whole time. All right, so let's see. For this first, now we just have to add up the distances on each half hour. So for this half hour, we've got a half an hour, and the vertical here gives me his speed, right? So my speed is 2, distance is, time is a half. So distance is rate times time. 2 times a half is 1. So what I've actually found is the area of this rectangle, right? Because I'm multiplying rate is what I get when I look at the vertical piece of that rectangle, and time is the horizontal piece. So when I multiply rate times time to get distance, I'm actually finding the area of that rectangle. So that can help me give a visual to keep track of what I'm doing. Okay, so for my underestimate, my distance traveled, I'm going to say rate times time, 2 times a half. Okay, and then let's look at the next rectangle. My next rectangle says that my rate is let's say 1.1, 1.1 time half an hour. So rate times time is height times base of a rectangle. 1.1 times a half. All right, and then my next rectangle, my rate is the vertical piece of it. Time is the horizontal piece. So that rate looks like a half, and my time is a half. So half times a half. All right, and then I have, what do you think? Is that 0.2 or 0.1? 0.1? Okay, so we have a height of 0.1. That's my rate. My time is a half. So 0.1 times a half. And then the next two rectangles are both 0. Oops. 0.1 rate times time a half an hour. And then my next two speeds are 0. So I have 0 times a half, rate times time, plus 0 times a half, rate times time. All right, then I move to the right-hand side of the parabola, and my values are going to be, my rectangles are all matching the rectangles on the left-hand side. They're all the same heights and same widths. So I'm just going to double what I already have, because I have some symmetry there. So maybe I'll get rid of this 0. So I take this whole thing and double it to get both sides of the parabola. Okay, so now I just have to have my calculator do this all out. Two times a half plus 1.1 times a half plus a half times a half plus 0.1 times a half plus 0. 1.85, and then I got to double it. 3.7. Now, notice that some of these numbers I estimated because the scale wasn't perfect, like this 1.1 and that 0.1, and also this half. So if you came out with something slightly different because you used a 1.2 or a 1.15 or something, that's fine for now. All right, so that would be an underestimate for how far Planck traveled, 3.7 miles. If I wanted an overestimate, I would overestimate his speed on each half-hour interval. Okay, so for my first half hour, instead of assuming he went the slowest that he went on that whole interval, I'm going to assume he went the fastest for the whole time. So I would assume that he traveled at 3 miles per hour for that whole interval. So that rectangle is going to represent my distance traveled. And then for my second half-hour interval, he started at 2 miles per hour and finished at 1.1 miles per hour. I'm going to assume that he traveled the fastest speed over the whole interval. So assume he stayed at 2 miles per hour for the whole interval. Okay, and then just keep choosing the fastest speed for the interval as you head across. And now I have 10 purple rectangles. Each one represents the distance traveled, an overestimate for the distance traveled over that half-hour interval. And then we would just add up the areas of these rectangles, because each area represents a distance. Because the area of the rectangle is a rate times a time, which is a distance. All right, so let's see, 3 times a half. And then the next one is 2. So we've got 2 and then 1.1 and then a half and then 0.1. 2, 1.1, a half, 0.1. Okay, so all right, and that is half the parabola. So I'm just going to double that rather than doing the other 5 rectangles. All right, so I have 3 times a half plus 2 times a half plus 1.1 times a half plus a half times a half plus 0.1 times a half. What did I do? And that was supposed to be a half. Thank you. 3 point, and then double it, yeah, thank you. 6.7 miles. Okay, so we have an overestimate and an underestimate. Does this make sense? Okay, good. So how do the estimates for the distance each zombie ran relate to the area between their velocity curve and the x-axis? Yeah, that's what distance traveled is. For Feynman, it was exact, right? Look at this velocity time graph. If I have time on the x-axis and rate on the y-axis, when I multiply rate times time, I'm really finding the area of this rectangle, and rate times time gives me distance. So in all of these cases, I was finding the area under the curve, or an estimate for the area under the curve. So our conclusion, which is the headline for today's class, is that distance traveled equals the area under a velocity curve. So if you have a velocity graph, the total distance traveled is the area under the graph. And we estimate it by making rectangles, by taking the speed and assuming you have a constant speed over an interval. So we can estimate the area under the graph. Whether we're given a graph or a table of values, we can estimate distance traveled. Okay, so here is a table and a graph. They both give the speed of a car that was traveling, and they give that speed in 10-second intervals over 1 minute. So take a few minutes, come up with at least an estimate for how far the car traveled in this 1 minute period, given this data about speed. All right, so let's look at this graph. If we want to get an underestimate, which endpoints of the intervals should I look at? The left endpoint or the right endpoint? The left, yeah, because the left one, if I look at a 10-second interval, in this particular graph, the left endpoint is always lower than the right endpoint because this is an increasing function. So to get an underestimate, I'm always going to use the left endpoint, the height at the left endpoint, to get the height of the rectangle, or the speed that we're assuming for that whole interval. Okay, so we're going to assume that this car was traveling at 35 miles per hour for this whole 10 seconds. Even though over that 10 seconds it actually accelerated from 35 to 50, we're going to assume it just stayed at 35. And this will give us an underestimate for how far the car went. And then from 10 to 20, I'm going to assume that it stayed at 50 miles per hour instead of changing from 50 to 60, whatever it is. All right, and then from 20 to 30, we assume that it stayed at a constant speed of 60 something. I can't tell by looking at the graph, but this table of values tells me the exact 61. All right, and then this looks like, I think it's 69 from 30 to 40 seconds. And then from 40 to 50 seconds, that's 70 something. I'll look at the table to find the exact value. And then from 50 seconds to 60 seconds, 70 something. 80 something, yeah. All right, so the area of each of these rectangles represents a distance traveled, an estimate for distance traveled. Because each of these rectangles, its base is a time, and its height is a rate. So when I multiply rate times time, I get distance traveled, finding the area. So this is going to be 35 times 10, which is 350 feet. Yeah, feet. Okay. And then my next rectangle, its base is 10 seconds, and its height is 50 feet per second. So I have 50 feet per second times 10 seconds is 500 feet. And then 10 seconds times 61, I think it was, is 610 feet. And then 10 seconds times 69 is 690 feet. 10 seconds times 76 is 760. And then 10 seconds times 84 is 840 feet. And then we just add those up. Okay, 350 plus 500 plus 3,750 feet. For the overestimate, I'm always going to use the right endpoint of my interval to create the height of the rectangle to assume the fastest speed over the whole interval. So the first interval started at 35, ended at 50. I'm going to assume that it was at 50 the whole time. So I've got this pink rectangle that represents distance traveled over that 10 seconds. Okay, so my pink rectangles are going to be my overestimates, always using the right endpoint to get the height of the rectangle. Okay, so this, my overestimate, is going to be the same as my under, except I have to get rid of that first rectangle and add the last big rectangle. And that last big rectangle is a height of, is 900, is an area of 900. Oops. $4,300, is that what people got? Okay, good. Overestimate 4,300 feet. So I could have just figured out the area of each of these pink rectangles and added them all up. I did a little shortcut because I said, oh, well, look at this pink rectangle, this first pink rectangle. It's the exact same size as my second purple rectangle was. And so the two sums are almost the same, except this little rectangle that was 350 square feet gets replaced by this big pink rectangle that was 900 square feet. So I just subtracted 350 and added 900. Okay, and then I saw a couple people went a step further and said, well, I have an underestimate and an overestimate. I could average them and get an even better estimate. Sometimes that's a good idea, right? In this case, because using purple rectangles was always an underestimate and using pink rectangles was always an overestimate, if I average them, I'll probably get somewhere closer to the actual area. $4,025. It's not always a good idea to average them. If the function wasn't always increasing, the left endpoints and the right endpoints won't always be under or always be overestimates. We'll see some examples where that happens. A better way, if you want a more accurate estimate, a better thing to do would be to take smaller rectangles, use smaller time intervals. All right, so here's the notation for finding the left and right-hand sums that we did in the past several examples. And this notation is the reason that I kept writing everything out, even though I saw your eyes glazing over and you were like, okay, I get it. It's the area of the rectangles. Because when you write it down with notation, all of a sudden it can look confusing, but it's the exact same thing we were doing with the rectangles and the numbers before. Okay, so we're letting v equal f of t be some velocity function. And I've just drawn sort of a generic curve here to represent any velocity function. And we're cutting this interval from a to b into n equal pieces. So a is going to be represented as t sub 0, and then I've got t1, t2, t3, up to tn, which is at b. So I'm breaking this interval a to b into n equal pieces, and I'm going to make rectangles on each of those little intervals. So the width of each interval, okay, if I'm breaking the interval from a to b into n equal pieces, what's the width of each interval? Variable for, oh, the total width would be b minus a, right? Yep. Yes. So this whole interval would be b minus a. So I'm going from a to b. And then I'm breaking it into n pieces, so this would be b minus a over n. Good. So that's the width of each interval, which is going to be the base of each rectangle. B minus a over n is my delta t, the base of each rectangle. All right, so then we can approximate total distance traveled, which is the area under this velocity curve. We could use a left-hand sum or a right-hand sum. You could also use some mix of the two, but it's much handier to just always do the same thing so you don't lose track of what you're doing. So if I use a left-hand sum, I'm going to make rectangles under my curve or over my curve, right? Rectangles that estimate the height of the curve using the left endpoint to get the height. So if I'm looking at this interval from t0 to t1, I'm going to use the left endpoint of the interval to get the height of my rectangle. And then I'm going to assume that height is constant over the whole interval. And then for my next interval, t1 to t2, I've got 2 points, a left endpoint and a right endpoint. I'm going to use the left endpoint to create the height of the triangle. And then I keep doing this all the way across using the left endpoint to get the height of my rectangle. So each rectangle is going to have width delta t. Right, so I've got delta t is my time interval, and then each height is a rate or a velocity. So I'm multiplying delta t times a velocity, time times rate. And f of t0 is the left endpoint of the first interval. F of t1 is the left endpoint, the height of the left endpoint of the second interval, etc. And then the last rectangle, its height is determined by the last point before b. So we call that t sub n minus 1. The last point before t sub n. And then when I do a right-hand sum, I'm just going to erase all this. Do it again for a right-hand sum. On this first interval t0 to t1, I'm going to use I have a left endpoint and a right endpoint. Use the right endpoint to get the height of the rectangle over that interval. T1 to T2, I use the right endpoint, T2, to create the height of my rectangle over this interval. And then I keep doing this until I get to the very end. My last interval, T sub n minus 1 to T sub n, I'm going to use T sub n to get my height, the right endpoint, to get the height of my rectangle. So then when I write down the areas of these rectangles, it's going to be delta t. Base of my rectangles will always be delta t, which is b minus a over n, times the height of the rectangle. And this first rectangle is going to have a height, f of t1. So we plug t1 into the function to get this y value, and that's going to be the height that you use for the whole interval. So when I use a right-hand sum, my first rectangle has height f of t1, and then f of t2, f of t3, all the way up to f of tn. Okay, because that last rectangle is going to use b, or t sub n, to get the height. So these are the formulas for the left-hand sum and the right-hand sum. You don't need to memorize them, because we found left-hand sums and right-hand sums all class without knowing these formulas. But understanding what this notation means will be important as we continue to develop finding area under the curve. All right, what do you think happens if part of your velocity function is negative? Why subtract? Yeah. A negative. Yeah. Yeah. So let's just say this curve, continued down like that, right? If I was looking at an interval and using the right endpoint, I would multiply delta t times this value, which would be f of some t, right? F of t sub I, f of t, whatever it is, would be negative. Right? So the area of that rectangle would come out negative, because delta t is always positive. This height would be negative, so the area of the rectangle would be negative. So if the velocity function is negative, area is negative, right? Which means distance traveled is negative. So velocity is has a sign, positive or negative. Positive would indicate movement in one direction. Negative indicates movement back the way you came. So if you have negative, if area is distance traveled and you have negative distance traveled, that just tells you how far back you went, right? So let's look at number 13 here. I have a velocity curve graphed. I want to find the distance traveled from t equals 1 to t equals 4 using this velocity curve. All right, so let's just look from 1 to 3. If I just want to find the distance traveled from t equals 1 to t equals 3, I'm looking for the area under that curve. And I don't have to use a left or right-hand sum to estimate because I can find that area exactly. How would I find it? Yeah, base times height over 2. That's a triangle. So from t equals 1 to t equals 3, my distance traveled is 1/2 times 2 times 4, which is 4. Right? So we went for, I don't know, units. There's no units given. I traveled 4 units from time 1 to time 3. And then I reversed direction, right? Because my velocity was positive here. I was slowing down, right? Came to a stop. And then I started traveling in the other direction from t equals 3 to t equals 4. So I'll do that in another color. So that area tells me how far I reversed. All right, so let's look at that. From t equals 3 to t equals 4, my distance traveled, the area of that rectangle would be 1/2 times the base times the height. And the height would be -2 in that case. Oh, it comes out to -1, yes. Yeah. So distance traveled is -1, meaning we were going backwards. We traveled 1 unit backwards. All right, so if I want total distance traveled, like if let's say these are miles, and I'm trying to tell someone how far I walked today. And I walked, say I went 4 miles to school, and then I realized I dropped something, right? And I had to walk back a mile. How many total miles did I walk? 5 miles, right? So my distance traveled, my total distance traveled would be 4 plus 1. Yeah, you just take the absolute value of that, and you'd get 5 miles. I walked 5 miles today. But there's another D word that's related to distance traveled, where we don't take the absolute value and we actually consider distance as a signed value. Anybody know what that word is? Displacement. So if I walk 4 miles in one direction and then 1 mile back, I can describe my position or my displacement from my starting point as 3 miles. Yeah. So my displacement is 4 minus 1, or 4 plus -1, which is 3. Does that make sense? So you have to pay careful attention to what question they're asking you, right? They want distance traveled or displacement. All right, so there's only a minute left, so I will not start the next section. We will talk about that next week.